So now we continue on this alteration method. In the previous two examples, what we did, and previous two examples and then the example before that on the expectation, what we used is that when we compute this expectation of certain random variable, and there exists a choice which yields that this value is like at least most t or at least t. Okay, that's good. But sometimes, I mean, this might not be, so let's say, so this means that there exists a positive probability. It's probability positive. You have SMOS T. Okay. And imagine some other situation. For example, if you have another random variable y, and then we want to say this is S. Then again, with probability positive, this y is MOS T. S. Somehow in this situation, we want both of them to be small. Of course, in that case, you consider x plus y as new random variable. Then this expectation, using expectation, you can say that this is MOS this. But its sum is smaller than that, does not guarantee both of them are smaller, right? One of them could be bigger than t, and then the other one is very small. Still, sum could be small. So we want, so imagine a situation that we want both of them to be small. Then you cannot say anything. This positive probability and this positive probability could happen on completely different instances. So in that case, maybe you are, in a situation that we want it to be small and it to be small, but it's not necessarily smaller than t and not necessarily smaller than s. It could be like at most 10 t is enough, and at most say 10 s is enough. And if we relax this, natural question is, can we get a better probability bound? If we somehow say that this is more than half and this is more than half, then you can surely say that with positive probability, both of them happen. What it means is that out of this discrete probability space, more than half fractions are good in this sense, and then more than half are good. Even if they are mostly disjoint, there should be some common element here, which yields both inequalities that we want. So this gives you some motivation on this. Once you know the expectation, can you get a better bound by relaxing this inequality? So that's the motivation for this Markov inequality. It's saying that if x is a discrete random variable, so meaning that its value is natural number, technically natural number together with 0, but non-negative integer, then what? The probability that x is bigger than certain number t is at most this expectation divided by t. Thus, if, write it this way, expectation of x goes to 0, then this implies that the probability that this becomes 0 go to 1. So that's, the proof of this is easy from the definition of expectation. What's the expectation? This is to take all k, because this is discrete random variable. It's its value is non-negative integer. So overall, for all non-negative integer, you consider the probability that this is k, and then you multiply k and the sum. And for this specific t, what? You truncate, you delete all the terms, which is at most t, then what? This is at least this. So you didn't do anything, you just delete the term, and then you decrease this to t. All the terms here, the k was actually bigger than t. So we replace with t, so this is smaller. This is what? This is t times the probability that x is at least t. So you get what you want. So using this, let's prove the following. Before, we have shown that there exists a triangle graph with arbitrarily large chromatic number. And when we were proving that, I mentioned that later we will prove the same thing with the probability method. But before, the proof was using this operation that provides a larger triangle graph with one higher chromatic number. But we can use probability method. Given A and G. And we can even prove the following stronger theorem. Not just triangle free. It's a triangle free and then no 4 cycle, no 5 cycle, no 6 cycle, dot, dot, dot. So there exists a graph with girth and list G. So I don't remember whether we defined girth, what girth means, but the girth of G is the length of shortest cycle of G. And we define girth of a forest which doesn't have any cycle. This is infinity. So we can find the graph with girth and list G and chromatic number and list K. So again, this shows that this chromatic number is not really a local parameter. Here, girth and list G means that no matter what G-1 vertex that we take, it induces graph with no cycle, so forest. So locally, it is forest, and the forests are always two colorable, but the graph itself could have a large chromatic number, so showing that the chromatic number is not really a local parameter. Okay, so what do we do? Again, we generate a graph at random, and let's say you have a vertex set bracket n vertex set, and by its we consider each pair of the vertices here be on X with probability P independently. Then what? What's the intuition? If P is large, then because no large independent set. So intuitively, it's clear. If we add more edges, then the largest independent sets shrink. The no large independent set. That means the chromatic number is large. On the other hand, if P is small, then if P is small, then the intuitively the number of short cycles should be small. very few short cycles. So what we do is that here we want to show that these two range of P overlap. There is a spot that is large enough to get large, this conclusion. And then while P is small enough to get this conclusion. Once you get such a graph, it has large chromatic number and then only very few number of short cycles. So you delete some vertices to remove all the short cycle, and you are left with what you want. That's our plan. So let P be the n to the t minus 1, where this t is 1 over g. Okay. Then, if you consider it, the possibility for each j cycle is you choose j vertices, and then they could induce a j cycle, right? So, since we can count the possible occurrence of j cycle, that are at most n to the j divided by 2j. So this is what? You choose one vertex, one vertex, one vertex, one vertex, j vertex, and then this is one possibility. But you might, choosing this in this order, and this in this order, and this in this order will give you the same cycle. Moreover, in the other way around, also give you the same way. So you choose at most n to the j tuple of the j vertices, and then out of them, 2j way give you the same cycle. So there are most this many possible j cycles, and each cycle appears with the probability p to the j. So this edge is there, this edge is there, this edge is there, all with the probability p, and then you multiply them. So let x be the total number of cycles of length less than g, as you can compute this expectation. It's a summation of indicated random variable over all these choices. So expectation of x is from I equals 3 to g minus 1. All those choices. And then you multiply the probability. And what? This is at most. So what? So what was P? P was this, right? So P was n to the minus 1. You take I, and wait, this is also I. So that's what? That's n to the ti over 2i. Since this t is 1 over g, what do we know? So this is at most g term, and each one of them is by most n to the 1 over g. So what do you know? By using this Markov, the probability that this is bigger than, say, n over 2 is what? By this Markov inequality, that's at most its expectation divided by n over 2, which goes to 0 as n goes to infinity. If n is large enough, this goes to 0. So for large enough n, this probability is smaller than half. So, okay? Again, now what? Since this alpha of g does not grow when we delete vertices, but in this process, you take the n vertices and then you delete the one vertex from each short cycle, and this independent sets are needed to color the vertices remaining after we delete a vertex of each cycle, each short cycle. So, but this means that if x is smaller than n over 2, then alpha of g is smaller than n over 2k, then what? This becomes bigger than k, bigger than or equal to k. Then the chromatic number of the final graph, then we obtain a graph with girth helix g and chromatic number helix k. So we want to show that these two can happen together. And we already showed that this probability is smaller than half. And then we want to now show that this probability is smaller than half. So let R be the 3 log n over p. Then what? The probability that the independence number of g is bigger than R is what? You can upper bound it. So what does this mean? This means that one of the sets of size R form an independent set, right? So there are this many such sets. Then for specific R vertices, the probability that none of the edges here means that for every one of them, it's non-edge. So non-edge happens for R choose 2 here. And this is a union bound. So this is the upper bound on the existence of set of size R, which is independent set. And this is smaller than what? Using the approximation, this is n times e to the minus t r minus 1 over 2 to the r. And this goes to 0 as n goes to infinity with our choice. Okay, then what? That's why we took the 3, which is bigger than half. So you just plug it in here, then this is smaller than n to the negative 3 over 2. Then this is a number going to 0. And then this is, so you can check that this goes to 0. So, what? Since this R is what? 3 times n to the 1 minus t, where t is 1 over g times log n. So that's how you get it by putting this p was this choice, right? So, and k is fixed. So we can choose n large enough so that R is more than n over 2k. So for such a large enough n, This means that for such a large enough and probability that the alpha of G is more than n over 2k, bigger than n over 2k, is more than half. So meaning that it's at most this is bigger than half. Together with this and this, so technically this is the probability that x is smaller than n over 2 is bigger than half. So we show that with positive probability, both of them holds, then that's exactly what we want to do. So there exists a graph, n vertex graph G with alpha being n over 2k, more than n over 2k, and having smaller than n over 2 cycles of length and most G, less than G. So we delete the vertex from its short cycle and obtain a graph with the girth LXG and chromatic number LXG. So this proves what we want. Okay, that's proof of what we wanted. And yeah, so far we have learned about this alteration method, which is useful. And next time we will learn a new technique called the robust local lemma, which roughly said that if you have a bunch of events and then their dependency is weak, then you can, with positive probability, you can avoid all of them at once. So that's what we will learn next time. Okay, thank you, and I will see you in next video.